All right. Good morning, class. This is, let's see, what is this? This is lesson 6. We will be covering section 1.8, linear transformations. This is lesson 6 for linear transformations. So keep in mind that homework 1 was due last night at midnight. So make sure if you haven't submitted that you want to go ahead and submit that. Each day late does drop by 10%. So if you haven't done it, try to make sure you have it turned in today. So you only have a 10% penalty instead of, a larger penalty, right? A 90 is still really good for a homework. So by all means, if you haven't done it, make sure you get that done by today. The penalty only becomes larger the longer it's late. So watch out for that. I'll be posting the information for homework 2 later this afternoon. So you'll have an entire week for that homework. Generally speaking, you'll see the way that I lay out the homework. They're exercises that are taken from each section as we cover them, which means if after we cover a section like 1.8, if you go ahead and do the exercise and homeworks on the homework as we go during the week, pretty much done, right? Generally difficult to try to do the night of their due, and you're going to set yourself up for failure if you're going to try to do that. These assignments are not things that you can just easily knock out in an hour unless you're really comfortable with the material and the vocabulary. It can be done, and of course some people have been successful doing that, but generally speaking, my recommendation is to work on the homework in increments as we go, as we cover each part of the homework. And I think you'll find you'll have more time, and you'll find you'll be less stressed about the homework in that regard if you space it out over a week instead of trying to do it all in one night. Okay, great. So section 1.8, what are we talking about? We are talking about linear transformations. Now, part of the reason I include this section next is because it very nicely piggybacks off of everything we've been talking about with regard to this matrix equation. So what do I mean? This is section 1.8, linear transformations. Right? What is a linear transformation? Well, first, let's refresh. What's the matrix equation we've been talking about? We've been having this equation A times X equals some new vector B. This, in fact, is a type of linear transformation. A matrix equation is, or may be thought of as transformation, where A, the matrix A, acts on X and transforms X into a new vector B. In other words, transformation is also another fancy term for a type of function. We can think of this equation as a function where what is my input? My input is some vector X. What is my output? Well, my output is what I get when I multiply A times X, right? I transform X by multiplying A times it, and I get a new vector B. So I have an input of an X vector, an output of a B vector, right? So this is what a linear transformation is. And we can see some simple examples, such as in this case. Let's suppose A is the matrix 1, 2, 1, 1. And let's say x is the vector 1, 2. Okay, well, what is a times x? How does it transform x? Well, then I need to do this multiplication, right? I can write this out as a dot product. So, or there's two different ways I can do this multiplication, right? Remember we talked about the dot product method. I can also write this as a linear combination, right? So the first option would be to write it as a linear combination. I have 1 times 1, 2 plus 2 times 1, 1. This is going to give me a new vector of 1 plus 2 is 3, 2 plus 2 is 4, right? Alternatively, we can also think about using the dot product, which says if I want to find the new entry, I multiply across the first row down the first column, right? So I have this first row 1, 1 times 1, 2. Well, when I do that, again, it's still a linear combination. 1 times 1 is 1, plus 1 times 2 is 2. For the second entry, that's the second row times the first column. 2 times 1 is 2, plus 1 times 2 is 2. In practice, both methods are going to get you the same answer, right? The reason I'm trying to stress this dot product method is because later, if like we're doing a multiplication where it's A times another matrix, which is not a single column, then trying to do it this way is going to be much harder. Of course, we'll talk about it more once we get there. But either way, we get the same result, 3, 4, right? So this then is the new vector b, which we get as a result of plugging in x and multiplying it by a. So we can have this visual representation of what we're talking about. So let me briefly draw that for us. This is the same idea as, let's suppose this big circle is all the different vectors in R2, right? Of course, R2 does not look like a circle, right? That's a plane, the XY plane. I'm just doing this circle to say that, let's suppose this circle is the whole space. Everything in this circle is everything that's possibly a vector in R2, right? And when I take x and multiply it by a, so I do a times x, I get a brand new vector b. Now, what space is that brand new vector b in? Well, that depends on the matrix A. In this case, b is also in R2, right? But depending on our transformation, it doesn't have to transform a vector from one space to the same space. It can go from a larger space to a smaller space. It could go from a smaller space to a larger space. We'll see examples of all of this. But the point here I want to start getting us familiar with is this idea that A can transform a vector to a new vector, and that can possibly be an entirely different space. In this case, it's the same. That's because we have a simple example here. Why does this go to R2? Well, taking this multiplication, we know this is the same thing as taking a combination of the columns, right? But because A is a 2 by 2, the number of rows here is telling me how many entries are in each column, right? And so the number of rows is telling me what space these column vectors are in. Because it has 2 rows, these columns are in R2. Well, if I take a combination of vectors in R2, the result of that combination is going to be something in R2. So in other words, the number of rows for your matrix A is going to tell you what space your B is going to be inside of, right? In this case, because A is a 2 by 2, X and B are actually in the same space. but it did transform x into a new vector, right? The vector 1, 2 and the vector 3, 4 are not the same vector. Okay, good. But does it always have to be the same space? Let's see an example where they go to different places. I didn't get any okay. Again, if you can't read the problem, so oh, that's going off of the board a little bit. Let me see if I can fix that. That's a little bit better. Okay, great. What about another example? Well, let's think about what if instead I have A is this matrix 4, -3, 1, 3, 2, 0, 5, 1. And let's say X. Now look, A is a 2 by 4, right? Which means in order to do this multiplication, in order to do A times X, well, then we know X has to have 4 rows, right? That's the only way we can multiply them. However many columns the left thing has, you have to have that many rows for the right thing. This is going to be a key point as we continue in the class as well. So X then is a 4 by 1. Why? Because I need a scalar for each column, right? In this case, let's keep it simple. Let's say X is the vector 1, 1, 1, 1. Okay. So right away, we already have this one difference. Where is my X? My X is now in R4. So my domain, what is domain? Remember for basic functions, for like a college algebra class, pre-calculus, or calculus class, domain is just referring to what is the set of possible inputs. Well, because A is a 2 by 4, my inputs have to be inside of R4, right? Okay, good. What happens when we multiply here? Well, when we do this multiplication, we have the matrix A times the vector 1, 1, 1, 1. And I'm just going to go ahead and write this out as the dot product instead of the linear combination. So I'm going to take the first row times the first column. 1 times 4 is 4. 1 times -3 is -3. 1 times 1 is 1. 1 times 3 is 3. Okay, that's going to give me the first entry. And then I'm going to have 2 times 1 is 2. 0 times 1 is 0. 5 times 1 is 5. 1 times 1 is 1, right? So my output here is going to be 5, 8. Right? This is then my B vector. This is the output vector. Now I also want to highlight here what happened. A, again, has 2 rows. And like we said with the last example, the number of rows for your matrix A is telling you what space your outputs are going to be in, right? So key point here. B then is still in R2. So what's happening? I'm plugging in any possible vector that's in R4. But when that vector in R4 is transformed by A, it becomes a vector in R2 with less variables, with less coordinates. So why are we interested in this kind of example? This seems kind of strange, right? We're going from one space where my vectors have 4 entries, and I'm somehow changing that vector into a new vector, which is now in R2. All right, so what's going on here? So part of the idea is you can think of, in computer science, there's this idea of file compression. Okay, what is file compression? Well, suppose you have some large file you want to send to somebody somewhere else, and you want to send it over a computer, over an email, but maybe the file is too large. It takes up too much memory to send it over email. It's too large of a file. That's an example of, say, something that's maybe an R4, R5, R6. It's something that has a lot more entries to it. It's too big of a file. So what's our solution? Well, it's too big to send to anyone. So we can instead compress that file into a smaller format. Now, of course, we have to be very careful in how we do that, because if I send them a crushed version of a file, then when they get it, we would hope that they would be able to decompress it. They'd be able to pull it apart into the original file, right? So file compression has to be done very carefully in a way that it should be reversible. These are all kind of ideas we're going to talk about later in the semester. I just want to get the ideas rolling now, since we will talk about it later. But for now, you can think of this idea as we're taking something more complicated, and I want to compress it into something less complicated. That would be one application of this kind of transformation. Okay, good. Let's see. Let's keep going. So now I want to talk about, what is the meaning here if we're trying to solve for x now? So before, when we were talking about the matrix equation, ax equals b, solving for x meant finding what combination of the columns of A, what combination of the columns of A equals B, right? And that's still true. Solving for x still means this. But now that we can think of this equation as a transformation, or in other words, we can think of it as a function, in an alternative way of what does it mean to solve for x, we can say solving for x means finding what possible x get mapped to b for, if you plug in, let's think about real 1 was mapped to 2 via the function. Same idea here. If you're solving for x, this means that you're trying to find out what possible x are going to get mapped to this b. Both of these things are saying the same thing. So part of what I want to highlight here is that as we continue, your textbook may have different exercises. It may word things in different ways, use different vocabulary terms, but you want to start putting these vocabulary terms together. You want to start putting these different forms together that are really saying the same thing. Finding linear combinations of the columns is the same thing as saying finding x that get mapped to a b, right? These are the same thing, and so we're going to solve both problems the same way. The only thing that's new here for 1.8 today is this idea of the word transformation. And the only other thing that's going to be new today is this notation I'm going to introduce for transformations. So let's look at the notation here. So notation because oftentimes this notation does trip up students the first time they see it. So I want to really spend some time talking about it. So we can say capital T is the transformation such that it maps things in Rn into Rm. Rn is then the domain, right? This is the set where my inputs exist. It then T maps vectors in the domain into the codomain. Now notice I did not say range here. This is because the range might not be everything that's over here. The range might only be a subset of the space you're going to. We'll see examples of this in a moment. So this is what this notation means. T is the transformation, right? So if I let x be in Rn, right? This is an x vector in my domain. Then T of x, this notation, it's the exact same thing as f of x, right? I'm just using the letter T instead of f. Same thing, nothing too spooky here, right? I'm plugging in x, and this is going to give me an output, b, which is in Rm. So the range of T is, well, what are all the possible outputs when I plug in everything from my domain, right? And this is a subset of the codomain. Subset, if you haven't seen this notation before. Now, the range being a subset of Rm, our codomain, it could possibly be all of the codomain. It could be the range actually equals Rm, but that's not always going to happen. We know we've seen examples where sometimes for some particular b, maybe a solution doesn't exist. Maybe there's no x which can be mapped to that b, in which case not everything in Rm necessarily will have a solution. But if everything in Rm, or not everything in Rm has a solution, then the range is not all of Rm. And we'll see examples of this in just a moment. Okay. Excuse me. Need to blow my nose real quick. Okay, apologies for that. I'm back. So let's look at some other examples. All right, let's suppose T is a transformation from R2 into R3, right? Okay, what does this mean? Big picture. That means I'm taking things in R2. This is my domain. These are where my x's are going to be. and they're going to be transformed by t to become new vectors in R3. Now, one thing we can do here is that this is enough information to tell us the dimensions of the matrix A. We know what sizes matrix A has to take on. Why? Well, remember, T of x, I'm transforming x by the matrix A. In other words, T of x equals A times x, which will equal the vector B, right? But in order to do this multiplication, I already know that my domain is R2, so x is a 2 by 1. Well, based on what we've said about what must happen in order to do matrix multiplication, because x has 2 rows, that means the matrix A has to have 2 columns. But then my outputs are vectors in R3. They're 3 by 1s. And remember what we said earlier, the space where your outputs are tells you how many rows you must have for A. So without doing anything else, just because I'm going from R2 into R3, I automatically know A must be a 3 by 2 matrix. Kind of a shortcut, if you remember it this way, flip them. That's what dimensions A must have, right? So A is a 3 by 2. And I haven't done anything else yet. I haven't told you anything else about A. All right, but for this example, I'm actually going to tell you what the matrix A is. A is the matrix 1, 3, -1, -3, 5, 7, and lo and behold, it's a 3 by 2, right? If it was not a 3 by 2, it would not work, and then it would not be a matrix we could use. Okay, great. So we'd like to know, okay, well, what happens when I plug in some x? Let's say an arbitrary x. What is T of x, right? So in this specific case, x is arbitrary. It's just some vector in R2 with an x1 and x2, right? x1 and x2 could be any real numbers. Well, that's okay. Without knowing what x1 and x2 are, I can still do this multiplication. It's just my answer is going to have x's in it, right? So again, I'm going to do the dot product, multiply across the first row down the column. I have 1 times x1 plus -3 times x2, 3 times x1 plus 5x2, -x1 plus 7x2, right? And without knowing what x1 or x2 is, there's nothing else I can really do here. However, what's nice about figuring out what is x when I plug it in, well, now for any kind of x to this and say, okay, what happens when I plug it in? So for example, let me erase my notation down here. Let's say u equals the vector 2, -1, right? Well, based on my formula here, I now know T of u equals x1, okay, that's 2, minus 3 times x2, well, that's a -1, right? 3 times x1, which is 6, plus 5 times x2, which is -1, negative x1, which is -2, plus 7 times -1. In other words, without doing any matrix multiplication at all, I'm just plugging it in here. Since I've already solved, no matter what the vector x is, this is going to be the output of the multiplication. This is going to be the transformation. So what do we get here? We're going to get 5, 1, let's see, -2, -7, -9. Right? And so this is then the result for plugging in u, right? Alternatively, yeah, you could have done the multiplication again and you would get the same answer. Excuse me. All right. And it's going to work out. Okay, great. What are other things, other questions that you could be asked here? Well, now we've already said that solving for x also means we're trying to find x to get mapped to a b, right? So we could ask the question, okay, well, let's let b equal 3 to -5. And we could say, all right, let t of x equal b, solve for b. Okay, well, how would we do this? Well, we're going to solve this the exact same way we've been solving matrix equations. What is t of x? T of x equals the matrix A times x. That's how we transform A. We're setting it equal to B. In other words, we're just trying to solve this augmented, or we're trying to solve this matrix equation, which we can do with an augmented matrix. So 1, 3, -1, -3, 5, 7, 3, 2, -5. All we need to do now is reduce this. So let's see. I'm going to take R2, and I want to subtract 3 times row 1. I want to take row 3, and I want to add row 1 to it. I'm trying to make a pivot right here in this first column, first row. And this will transform into 1, -3, 3. For the second row, we're going to have 0. -3 times -3 is a +9, so 14. 3 times -3 is a -9. So when I add here, we're going to get -7, if I've done this correctly. Yeah, I think so. -3 times 3 is -9, -7. Good. I'm going to add row 1 to row 3. So 0, 4, -2. Okay. Now in this current form, I know I would like to get a pivot possibly here, but right now trying to use 14 is going to be really, really messy, right? I don't want to have to do that. So what can I do instead? Well, notice for row 2, both entries of row 2 are multiples of 7. Recall that each row is really just an equation, right? So if I wanted to, I could just take the row and divide both sides by 7. I would get 2x2 equals -1, right? If we do this, it can make row 2 a little bit easier to work with. But by the same reasoning, I can take row 3 and divide it by 2, right? So I'm going to take row 2. I want to take row 3, and I want to divide it. Now I have 1, -3, 3, 0, 2, -1. 0, 2, -1. Well, now in this cleaned up fashion, I can see, well, if in this very last step, I just take row 3 and I'm going to subtract row 2 from it, then it's going to be nicely cleaned up. So let me make some space here. This very last step, then, we're going to have 1, -3, 3, 0, 2, -1, 0, 0, 0, and we're done. Or at least this is echelon form. If you wanted to go further, yeah, you could put it in reduced echelon form. It might get a little messy with some fractions, but remember, echelon form is enough to answer the question. Why? Well, start from the bottom. Okay, row 3 doesn't tell us anything. First of all, this is consistent, right? There's no pivot in the equals column, so a solution exists. Great. There's an x that can be mapped to this b. Okay, what's x2 though? Well, take row 2, and we see x2 equals -1/2. All right, great. What does that tell us about x1? Well, this equation for row 1 says, let me put that in a box, x1 minus 3, x2 equals 3. Well, plug in now what I know for x2. This is why start from the bottom of your matrix when you're trying to solve for your entries. Don't start at the top. Start from the bottom and work your way up. x1 minus 3 times -1/2 equals 3. So I have x1 plus 3/2 equals 3. I need to subtract it over. x1 equals 3 minus 3/2. Or in other words, x1 equals 3/2 is just the same thing as 1.5. 3 minus 1.5 is 1.5. So x1 is 3/2. And I have my solution x. This is the vector. When I plug it into t, gets mapped to this b. I think I erased it over here, but it was this equals column. This was the vector b, right? This x gets transformed and mapped to this b. Something for 2 gets mapped to R3. So in this case, we can see that, oh, well, it looked like I had a solution for this b, right? However, am I always going to have a solution? So let's see. Yeah, we'll do one more example, and I want to give one more definition, and then we'll wrap things up here. Right. Do we always have a solution? Well, what if instead we have C equals 3, 2, 5, right? And we want to we want to ask, find x such that t of x equals c. So it's the exact same problem we just did, except instead of the b vector, I want to augment with c. Well, all right, here's my matrix A, 1, -3, 3, 5, -1, 7, augment with C. And for the second time, I'm just going to jump to what the reduced row echelon form is. You can check the details of this, make sure that you understand how to reduce a matrix correctly. But if you get this matrix in reduced row echelon form, you're going to have the matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. Well, what happened? I got a pivot in the equals column. And this last row says 0 equals 1. This is inconsistent. And again, this is a phrase, a word, a vocabulary term we can only use with augmented matrices. If your matrix is not augmented, you can't say whether it's inconsistent or not. So what does this mean? This means there is no solution, right? In other words, C is not in the range of the transformation T. So we have this case. T is a transformation from R2 into R3, right? But we found a B such that T does not map to that, or T has no vector X, which can map to that vector C here, right? In other words, the range is not all of R3. The range of T does not equal R3 in this example. Sometimes your range can equal everything that's over here, but in this case, it doesn't because we just found an example that's not in there, right? So how would we know if it's in there or not? Well, in order to hit everything in R3, R3 is three-dimensional, right? Which means if I want to span all of it, I'm going to need three linearly independent directions I can move in. Well, how do I know how many directions I can move in? Look at the matrix A. How many pivots does A have? If A has three pivots, then it can span R3. In that case, the range will equal R3. But in this example, A was a 3x2. I can only have at most two pivots. And in fact, these vectors are not multiples of each other. So we can tell that for the matrix A, these are linearly independent, but I only have two. I only have two pivots. So at best, all the possible linear combinations of these columns, in other words, all possible outputs of my transformation T, can only span a two-dimensional space because I have two pivots. Now, does that mean the range is in R2? Does that mean the range equals R2? No, right? The dimension of a span has nothing to do with what space you're inside of, right? Let me say it again. The dimension of your span has nothing to do with the space you're inside of, right? Combinations of these columns are in R3, right? Now I only have two of them, which means their span is two-dimensional, meaning I have a two-dimensional space inside of R3. It's not in R2. It doesn't equal R2 because these vectors are in R3, right? So what does that mean? That means the transformations, all these outputs, is a two-dimensional space. In other words, all of this range is some plane in R3. It's some piece of paper. It's some two-dimensional plane in R3. That's what the range is for this example. So for that reason, the range is not going to equal all of R3. Okay, so what happens when it does equal R3? What happens when it doesn't? These are other special terms, special ideas. We're going to talk about more in future sections. All right, there's two other things I want to highlight here. There's one other definition I want to give you real quick, which can be helpful for some problems. And then I also want to go over today's participation question. Okay, so first of all, I want to note some special properties here. So let T be a transformation from Rn into Rm, let lowercase u and v be vectors in Rn, okay? What happens if I try to transform u plus v? Well, there's two ways you could go about trying to solve something like this. One, you could figure out, okay, what is the vector u plus v? That then becomes a single vector, and then you would be good, right? You would have a single vector, and you can multiply it by the matrix A. However, I want to highlight a special property with these linear transformations. This is the same thing as the matrix A times u plus v, correct? But remember, with matrix multiplication, I can distribute this matrix the same thing as A times U plus A times V. In other words, what am I highlighting here? T of U plus V is the same thing as T of U plus T of V. So T of U plus V is the same thing as find T of U plus find T of V. You can break it apart like this. You can distribute T over what you're plugging in. What's special about this is what it means to be called a linear transformation. If you've taken calculus, the integral does the same thing, right? If you have the integral of two different functions being added together, right, you can break it apart into two pieces. In fact, the integral is also a linear transformation. You would have heard that and seen that in calculus class. The derivative is also a linear transformation, right? These are all examples of other types of linear transformations. But the point here, matrix multiplication is just another linear transformation that allows us to do this trick. Similarly, what else could you do with integrals or derivatives? Well, you might remember if you have an integral with a constant times a function, you can pull that constant out. It's the exact same thing here. Let C be a constant in R. Then what is T of CU? Well, this is the matrix A times CU. But remember, with matrix multiplication, when C is just a constant, I can change the order in which I multiply things. But now that's really just the same thing as C times T of U. So constants, I can pull outside of the transformation. This is what it means to be called linear. Okay, so a transformation. Let's see. Did I run out of space? Is that still on the screen? Good enough. Okay. A transformation is linear if for any u and v in your domain and for any constant c in R, we have one. First of all, you can pull them apart, right? T of u plus v is T of u plus T of v. And two, T of cu, you can pull the constant out, right? So remembering this property for what it means to be linear, this is going to be super important. You want to remember this. It's going to be helpful later in the course. I've also been known in the past midterms and tests, I've asked questions about what it means for a transformation to be linear and how you can use that to solve things when you plug in vectors, right? So you want to hold on to this, save this away somewhere. I have been known in the past to ask test questions about this idea, this definition. Okay, let's quickly change over to the participation question. This is participation day 6. Let me share my screen. Let's see, here we go. All right, should be sharing. Participation day 6, here we go. Suppose T is a transformation. Let me zoom in a little. T is a transformation from R5 into R2. Again, remember, before I even think about the rest of the question, if I flip the numbers 5 and 2, that's going to tell me the dimensions of A. So A is a 2 by 5, right? Okay. And T of X equals A times X for some matrix A and for each X in R5. Again, this is the domain of the transformation, this R5. And so X must be in R5. X is a 5 by 1. That's how we know A has to have 5 columns. So how many rows and columns does A have? Oh, great. We've already answered that. A is a 2 by 5. So A has 2 rows because it's a 2 by 5. And that's it for today's question, right? You're going to submit that and you're good. If you have other questions, please feel free to let me know. Email me. Office hours began last night. We had our first Zoom meeting last night for office hours. I'll also have office hours tomorrow night. So from here on, it's going to be every Tuesday, Thursday, 6 to 7 p.m. Just click the Zoom link on Canvas when it comes time, and that will automatically connect you to my office hour that's over Zoom. Otherwise, best of luck. Homework 2, I'll post later today, so you can go ahead and get started on that based on what we've covered and talked about today. Otherwise, have a great day. I'll see you tomorrow.